Right, I think it's time to start. So thank you all for joining us today to discuss building secure IIoT solutions. And discussing both the challenges the industry face with the most commonly used protocols, but also the solution that we can help overcome them. First thing first, I'll introduce you to our guest speaker, Xavier Mesribia. He has got a very vast amount of experience when it comes to IIoT applications and working with the industry leaders in this.
Good afternoon, everyone.
Thank you, Xavier. So currently, everybody is on mute because we are in a webinar environment. But what you can do is to send us a question in the chat or raise your hand using the web tool. And if you have any burning questions, we'll try to accommodate that. It is an interactive session. Me and Xavier will be having a chat with each other. So we introduce you to if you have a question, just by all means let me know. Copies of the presentation and webinar link will be emailed to you at a later communication. So don't worry, we'll send you a recording and the copy of the PowerPoint. So to start with the agenda, we will be discussing what are the risks of IIoT, identify the most commonly used IoT protocols and give you the pros and cons, and then honing on to the MQTT standard, which is the most common one out of them all, and then talking about the added bolt-ons to the MQTT standard, the advantages, the challenges, and how does DataHub help in all this, and we will just do a case study and then open the floor for more questions. Right. So as the IoT is getting more popular, more companies are implementing IIoT solutions. This requires sharing of data from the control plant network. When sharing takes place, more attack surfaces are exposed. Now, this can be because the traditional methods used were never designed with this type of security in mind, or a poor implementation of the standard. And for those reasons, where we see that there are risks associated with the IoT, and we've seen in the recent past events where malicious activities have happened. A recent example is ransom attack on a US gas pipeline, where there was outages. Honda confirmed a global attack on their operations, and that's just because one of their sites got attacked, and because of the traditional methods of security being used, the global operations got affected. And then there was a hacker who tried to poison Florida through their water supplies. Now, this is where you step into the public domain, and for that very reason, the governments are getting involved. They are trying to guide the organizations and the public bodies to start taking this operational security more seriously. And in a very rare joint release by both CISA and NSA, they recommended immediate action to reduce exposure across operational technologies and control systems. And due to the recent attacks, the European Commission had to revise their directive called the Security of Network Information Systems 2, and their key guideline is to have more DMZs in the architecture. So it's more secure, manageable, scalable. The segregation between the control side and the corporate side is giving that air gap, so you're not prone to these attacks. Even if you get the attack through, it is not at a global scale, as we've seen in the previous slide. So here, what I'll do is I'd like to invite Xavier to shed some light on the lesson learned by the lack of IIoT security and the gaps in there.
Thank you, Abdul. So what we've learned over the last few years is that victims fail to implement robust segmentation between their OT and IT networks. And so by not having a robust segmentation, what happens is that the adversary will enter either the IT network, usually through the IT network, and then from there they can access into the OT network to compromise their HMIs, their data historians, their polling servers. PLCs are very, very rarely attacked. We did see those instances a few years ago. But what's most important is that for international companies, the impact, as we saw with Honda, is not geographically limited. It affects all of their systems, and it can cost millions of dollars to repair.
Right. So what we're going to do is we're going to take the Purdue model, and I'll ask Xavier to take us through it and show the different, and talk about the different layers of security that are generally implemented within OT-IT environment and integration. And then obviously talk about the VPN side of things. In our previous webinar, we've spoken more about the Purdue model, but Xavier, if you can quickly take us through this.
Right. So for anybody who's in industrial automation, this should not be new to them. The Purdue model basically defines what the architecture should be from a secure standpoint. So what we've added on this is the firewall. So to have a secure environment, you still have your firewalls. But the challenge is that if you look at the arrows, as an example, if I'm moving or trying to collect data from level 3 or level 2, what happens is that I'm actually having to open an inbound firewall port because the client must connect to the server. And so when you look at the Purdue model, the challenges you have is that in fact it has your segmentation, but you're also pushing downwards, opening up firewall ports. Now, when you add a VPN, which is what many people do, is they'll add a VPN. VPNs actually don't solve the problem. They actually make it worse because anyone in the VPN has access to, or any computer in the VPN has access to all the resources to where the VPN is going. So if I'm going from level 5 to level 2, then anyone on that VPN now has access to all of the computers in level 2. So if the adversary enters via level 5, they now have access to level 2, and then ultimately they have access to 3, 3.5, and 4.
Right. Thank you, Xavier. Again, that leads to a very important question. If that's the case, but then what are the best practices to actually work in the OT-IT integration environment, and what are the best practices given by these government guidelines? So can you give us a recap on that, Xavier, if that's...
Sure. So the key is that you want to keep your firewall ports closed. You want to eliminate all VPNs on your control network, and that's just prudence from the standpoint of, if I have open firewall ports, then I have a way for an adversary to get in. You really should be segmenting your network control system, as we showed earlier, from level 1 through to level 5 with firewalls. And you should also be using DMZs whenever possible to bridge the network level. So adding a DMZ creates a layer of security that isolates one network from the other. And so adding these DMZs within the levels makes it much more difficult for an adversary to get in. Never provide internet access on the control network. And probably most importantly is never do it with a mail server. 80% of the adversaries enter through email. So if you have access to email in the control network, then you are setting yourself up for failure. Connecting to cloud services, the same thing. To connect to a cloud service, you have to have internet access. And so you really want to avoid providing internet access on the control floor. Other best practices really are to keep your firmware and software up to date. The old philosophy was it's running, it's working, and we're not going to change anything. And so that's why we have many, many companies out there running Windows XP still. Well, the problem is Windows XP security was never designed for today's adversaries. And so you really do need to keep your software and hardware up to date, because as adversaries get stronger and they approach things in different ways, both software and hardware companies also come up with fixes to prevent these things to happen. And so it's really a cat and mouse game, but if you're not in the game, then you're really keeping yourself exposed. Finally, back up your systems. And so keep your system backed up. That's great, but keep them disconnected from your network. There are, proper backup procedures where you run a 7-day backup cycle, and you take the 1-month backup, you put it in cold storage. You want to run a series of backups, because if you're hacked, you need to have a plan, and that plan requires you to have a backup to bring your systems back up to speed.
Great. And just keeping these best practices in mind, we're now going to be discussing very shortly about the IoT applications or the protocols that are being used in the industry at the minute, and how do they actually work around or work with the network segmentation and firewalls. So
right.
Just talking about this briefly, as a solution, when we're looking at creating or building IIoT solutions, what we want to do is we have to keep security in mind. We don't have to have or allow any attack surfaces that can be exploited. But at the same time, what we want to do is we want performance out of the system. We don't want to slow down the performance, because the industrial data is real time. And if you are talking about real time communications, the data is lost as soon as it's changed in the industrial side of things. We need to have some sort of no data gap solutions available. Then we also have to have the flexibility. It doesn't add an enormous amount of integration cost. It doesn't interfere with your ongoing processes. It just streamlines your whole transition phase. Now, before I head any further, we're going to be doing a poll, and this poll is around the most commonly used IIoT protocols. Before I ask Xavier to go and explain these in more detail, I'll just put a poll forward, and that is: do you think OPC UA is a suitable protocol for IIoT applications? So I'm going to keep this poll open for a minute or so. Right, so we've got 60% votes, so I'm just going to leave it open for another 20 seconds or so. If you can please kindly vote. Okay, so we've got the results back. I'm just going to close the poll and share the result. Can everybody see the result? Xavier, can you see the result?
Yes, I can.
Yeah, so 60% of our audience today thinks OPC UA is a good way of getting started with an IIoT application. We'll see. We'll see what happens when Xavier explains us using this comparison chart. Just before we head any further, again, I'll put another poll out there, and that's: are you familiar with MQTT? Just if you can quickly answer that question for me in 30 seconds or so. So this poll will give us an indication of how much the audience knows about this protocol and how much in depth and detail we need to go into. Right, so we've got the results. So majority of us know what MQTT is. 40% of us don't know what MQTT is. So yeah, we can go into a little bit more detail into the protocol itself. Now, one last poll, which I would like to do, is around Spark Plug B. do you know about Spark-Plug-B? Right, so I'll just keep it open for another 20 seconds or so, and just kindly vote. Right. So we've got the results, and as expected, exactly, we have a majority of audience who don't know about Spark-Plug-B, so we can go in a little more detail about Spark-Plug-B when we introduce this or do the comparison. All right, so what I'll do is I'll give the stage to Xavier, and over to you.
So one of the questions had to do with OPC UA and is it a valid IoT protocol? And so when you're taking a look at protocols, you kind of have to look at coming back to those the key architecture questions about opening up firewall ports. So one of the key things or failures of OPC UA is it does require an open inbound firewall port because the client is connecting to the server. And so the net result is that is one of the challenges. So when you're looking at IoT protocol, we have certain things that we're looking for. So closed firewalls, low bandwidth, low latency, the ability to scale. Should it be real time, interoperable data formats? How do we handle intelligent overload handling? So if a broker is overloaded, how does the system manage it? Propagation of failure notification. So if there's a failure in the write or a failure in the communication, how is that propagated throughout the system? And then ultimately quality of service. So each and every one of these protocols have their pluses. So for instance, MQTT and Spark-Plug-B have the ability to keep or push data out to a broker. Thereby, they don't require an open inbound firewall port. They are low bandwidth, they're low latency, they do scale well. AMQP, which isn't often talked about anymore, does also offer the same. But OPC UA does have some challenges in the sense that it does require an open firewall port. It is low bandwidth and low latency. It's partial, true, but in terms of the ability to scale, again, it's also very resource intensive. They're real time. OPC UA is real time. MQTT and Spark-Plug-B are not real time. They're messaging protocols. So is there an interoperability format? So in the case of MQTT, the answer is no, because it's an envelope. What's in the envelope is not a standard. With Spark-Plug-B, there is an interoperable format. It is the partial, but it's not as pronounced as OPC UA, for instance. And in terms of handling, all of them fail in the sense that if there's too much data coming through, MQTT just throws data out. Same with Spark-Plug-B, AMQP does the same. OPC UA, it will just be clogged. And so the net result is it will literally lose data as an ongoing basis. But more of the most concerning area is about this daisy chaining. So when you're daisy chaining from level 2 to level 3 or 3 to 3.5 or 4 or 5, you're actually going from one to another. And that's where you have challenges because MQTT and Spark-Plug-B can do it, but it's extremely fragile. And we'll talk about that a little bit later. And then the propagation of failure notice is also extremely fragile as well for MQTT, AMQP. And then obviously the quality of service, UA does a much better job than any of the other protocols. Okay.
Yeah, thank you for a quick comparison between the most commonly used IoT protocols, which most of the people are basing their IoT applications on. OPC networking. We've done this is the second webinar for a 3-webinar series. So we did our first webinar on OPC networking and its challenges. So if you want to know more about how you network OPC UA or OPC in general, and how do you actually overcome the challenges we just explained, then please kind of refer to that. And if you want to get in touch, then please do so. I'll share my details at the end of the webinar and we can have a conversation about that. So moving on to the MQTT. Now, we had a significant amount of audience that said they don't know about MQTT. So we'll start from the very basic. So exactly, if you can just take us from the basic of MQTT, and we'll take it to the architectural level in the next few slides.
Sure. So MQTT is an OASIS standard of network messaging protocol for the Internet of Things. That's how they describe themselves. It's a publish and subscribe messaging transport. The advantage is it's lightweight and efficient. It's bidirectional communications, and it really offers 3 levels of defined quality of service. And think of quality of service as, did my message get there? So level 0 is at least 1, so i.e. I submitted the message, but I'm not waiting for acknowledgement. Level 1 is I sent the message at least once, I got some acknowledgement that somebody did something with it or that it got received. And level 2 is I sent the message, I get a confirmation that I sent the message, and then I confirm that I received the message. So it's truly exactly once that message is received.
Right, interesting. So how does this protocol actually work? So exactly, you can just take us through this architecture of a typical MQTT in a communication happening between a client to a client.
So typically you have an MQTT client, so in this case a temperature sensor. It is publishing data to a broker. That we would also have a SCADA client who is also subscribing to the topic of the client. So the net result is that the client is subscribing to the broker, and then the SCADA system, in my example, would be subscribing to the broker as well. Each one of them has their unique capabilities. So they're both subscribing to the data. We might also have back-end systems. So again, we have another client connecting to the broker, subscribing to the topics. So the connections are one-to-one to the broker. So the client to the broker is a one-to-one connection. The data is one-to-many. So I can have many clients also connecting to that subscriber. Should the client, so for instance, in this particular case, should the client in the temperature sensor fail, the challenge with MQTT is that there is a defined last will and testament message that's published by the broker. But that last will message is normally an MQTT message with a topic. It's a retained message flag, quality of service, and payload, which is in fact not connected to the same topic. And so the net result is that any connecting client has no idea that in fact that client disconnected.
Right. So we'll come to the challenges, but I believe the new bolt-on standard on top of MQTT is a Sparkplug B, and it tries to address this inherent problem with MQTT.
Right. And so Sparkplug B attempted to solve this issue of communication. And so by doing it, they've changed some of the nomenclature. So in MQTT, you have what's called an edge of network device. And so typically in the architecture, you have an edge of network device, or what they call a publisher, who is writing to or sending data to a broker. You then have, in the MQTT protocol, you have the one primary application. And so that primary application subscribes to the topic of the broker. And then you would have non-primary applications that would also connect to the topic of the broker, such as, in this case, the temperature sensor. The SCADA is considered a primary application. The backup system is a non-primary application. Now, if we have an ungrateful disconnect from the sensor, then the last will and testament is strictly defined so it's connection aware, which means that the primary application will know that the edge of network failed. So that's a good improvement over MQTT by far.
Great. So let's talk about the advantages now of using MQTT.
Sure.
Yeah.
So MQTT, there are some tremendous advantages. First of all, it's a publish and subscribe messaging transport, which means that I'm pushing data out. I don't require an open inbound firewall port. So the MQTT client or the edge of network establishes an outbound connection. It's lightweight and efficient, so typically uses less bandwidth than traditional OPC. So unless there's a disconnect. When there's a disconnect, then the client or the edge of network will send all the data again. So all of a sudden you're hit with all of the data. It is scalable, which is great. It's battery friendly, so typically well suited for low power devices. And you'll find MQTT commonly used in water and wastewater.
Okay. Now, we know for a fact that MQTT solves a lot of problems in the industry, but when we, but it's kind of, as you explained, it's kind of a few verticals where MQTT is proving more beneficial than others.
Right.
And that's due to some challenges. So let's talk about some challenges then.
So one of the big ones is that MQTT is a messaging protocol. It's not a data protocol. So MQTT does not offer a standard data protocol, which means that if you have multiple devices out on the network or MQTT clients on the network, you have to make sure that they're all talking the same way to the broker, if you will. The broker cannot perform intelligent routing. And this is probably one of the big things, is that it doesn't maintain message order. And so it is possible in MQTT where I have one message that comes in and says the temperature is 10 degrees and another one says it's 15, and those could be swapped in order. And so since the broker can't intelligently route the messages, you have no way of knowing which one was first. So there's no guaranteeing consistency. Daisy chaining is not reliable. And so think about it this way. If I have a client connecting to a broker that's a client connecting to another broker, each one has a quality of service. And so that quality of service does not chain between brokers. And that can create problems, because if I'm using level 2, if I'm using QoS 2 between the first client and the second one, I have to maintain 2, but then my message order gets completely messed up. It's difficult to restrict access to topics or set them as read-only. With MQTT, you're sending data and you can receive data, but it's very difficult to control access. In fact, just a simple hashtag on the topic, on the root topic, will give you access to all of the data. Quality of service is a bit misleading. In quality of service 0, there's no guarantee of delivery. In 1, this level makes sure that the recipient receives the message at least once, but there is a possibility that a duplicate messages are also received by the recipient. And quality of 2 this level's guaranteed that each message is received only once, but the problem is scalability, because you're sending 4 messages for each message. And so the net result is that you're dealing with a bandwidth restriction.
So effectively, if you want the data, if you want that data to be there exactly once, we are producing a lot of network overhead.
Right.
Again, there was something we spoke about, a Spark-Plug-B, but it has got its own challenges in industry. What are the challenges you've come across, Xavier?
So Spark-Plug-B, again, is, it cannot route based on package content. Again, the broker is not intelligent. It just acts as a broker. It acts as a relay. And so it doesn't maintain message order. In fact, the specification says it doesn't have to. Daisy chaining for Spark-Plug-B is also the same problem with standard MQTT, is that quality of service between the broker and the client. We also have difficulty in restricting access to the topics, i.e. read-only or data sets. And then there can only be one primary application. And so this is one of the critical downfalls of Spark-Plug-B. And that is if the edge of network device disconnects, there can only be one primary application to report it. Non-primary applications are not allowed to talk to the edge of network device. They're allowed to subscribe, but they can't talk directly to them. So the edge of networks do not know if their messages are received. They just know they've published them, but they do not know if they've been received by the primary application. And then non-primary applications must not publish their state. So if my non-primary application is, for instance, writing to a database, I can't publish my state to say that I have, I'm now disconnected. And so that's one of the challenges. And then if the non-primary application connects after the edge of network, you'll never see the node, i.e. you'll never see the data. And so you have to be able to force that node to reconnect so that you could see the birth message. And so with Spark-Plug-B, there's this concept of a birth message. The edge of network sends its birth message, which is then received by the primary application and the non-primary application and say, hi, here's a new device on my network. If you don't receive the birth, then you don't have a way of identifying the device, and so the data is just, dropped.
Right. Thank you for the insight there, Xavier. Thank you very much. So just a quick recap, just to see how MQTT and Spark-Plug-B match to each other. I think there's only one thing which Spark-Plug-B resolves here, and that's the interoperability data format. So just in a brief few words, if you just elaborate that would be great.
I totally agree, and that is actually the main thing of Spark-Plug-B is that interoperability. So any device that's using the Spark-Plug-B standard should be able to communicate with the primary application. So that is one of the advantages. Otherwise, they're pretty much the same.
Okay, so all we're saying is that Spark-Plug-B is a little more state aware of the publisher or the edge of network device.
Correct.
Okay, thank you. Right, so how does DataHub help, in this kind of situation? I know for a fact that DataHub is a smart broker. So how does this pan out with DataHub?
So DataHub, if you look at the protocol, the way things work, DataHub's a little bit different in that you would have the DataHub as the DataHub broker, but it's a smart broker. And so you have your client connected to your broker, your SCADA system in this particular case connected to the broker, and you would also have your backend systems or anything else connecting to the broker as well. So you basically have the same architecture. The difference is that the DataHub smart broker is one-to-many. So each connection status is shared with all connecting clients. So in the case of MQTT, if the client disconnects, the DataHub is assigned a status to every data point on that client, and it shares that status with every connecting client. So the net result is that your messages, you now know that the client disconnected. It will also maintain message order. So the DataHub will maintain message order to your SCADA system or to your backend systems. In the conversion from MQTT to OPC UA or DA is built in. So if I'm connecting to a SCADA system that's a UA client, I can now it will deliver the MQTT data or the OPC UA data with no delays. And all the security is built in. So now I can actually control what information I want to share or what information I do not want to allow to go bidirectionally. And then finally, should the client disconnect, the connection status of point quality is displayed for all subscribers. And so that's one of the key differences between what the DataHub broker does and your standard off-the-shelf open source brokers. For MQTT Spark-Plug-B, again, if we look at the topology, this time we've injected the DataHub into the broker. We have our SCADA system, which is our primary application. We have our backend system for non-primary application. So it is, again, data aware. So unlike MQTT brokers, DataHub is aware of the data that is being transmitted. And so that allows us to solve a few things. It responds to errors. If we have a delivery problem, it responds to delivery and startup problems. So if the edge of network or if the non-primary application connects after the edge of network, the DataHub sees it. It will force the edge of network to republish its birth. It resolves failed writes to devices. It'll detect out of order messages, and it will manage late connection of non-primary applications. So again, if there's a late connection, the DataHub will initiate the birth message to tell it these are the items that you're connecting to. And then finally, we support OPC UA, so a more consistent integration to your SCADA and your backend systems. So if you want to use, most SCADA systems will use DA or UA, we can now just turn around and say, well, we'll deliver it to you in UA, which is much more reliable and much more consistent to what the SCADA system is looking for.
Brilliant. Just to remind everybody that this is an interactive session, so if you've got any questions, you can write them in the chat. Or you can raise your hand and I can unmute you and we can have a discussion over this. So starting with that, to begin with, we mentioned that the governments do get involved, and one of the guidelines the governments are given is that we should introduce DMZs. And let's talk about that so you can make the right choice for the solution you're looking for. So Xavier, a typical application would be that you have the MQTT client sitting behind a firewall and you're connecting to the cloud, but you don't have a DMZ in there, right? So if you can just explain how we can make the systems more secure and more reliable.
So one of the advantages is that, if I'm sitting in the plant source, I can move an outbound into the cloud. That's not a problem. But the issue is in order to see the cloud, you have to have network mapping to the internet. And so most plant networks do not have access to the internet. So in a typical environment, in order to make this work, you would have to map internet access into the plant, which most people would not do, and it certainly isn't secure. So the other option that people have looked at is, well, what if I put the MQTT broker in a DMZ? So again, I'm pushing data from the client to the DMZ, and then I get the cloud client to connect. Well, the problem here is that moving the broker to the DMZ solves the security issue, but it does require the cloud service to connect to the broker. And so most cloud services like Azure, AWS, Google, they're not clients, they're brokers. They expect to see the data. So what other people have tried to do is say, okay, well, you know what? We could say, how else can we do this? So DataHub can do a unique thing, and that is the ability to mirror data. So internal to the DataHub, we use a protocol called DataHub Transfer Protocol. And what it actually does is mirror the data from the OPC client to a DataHub sitting in the DMZ. And so the net result is that there is no inbound firewall port, there's no VPN, so I'm secured on the plant network. I don't have access to the network, I just have access to the data. And then from here, we push outbound to the broker. So again, the data can be bidirectional, but the two networks are completely isolated. The plant doesn't have access to the internet, the DMZ does. And so data is published to the cloud using MQTT from the DMZ, so there's no inbound firewall ports, there's no attack surface, everything is completely secured.
Great. That's much more smoother and easier to implement, isn't it? And plus, with the data being in the DMZ in real time using DHCP, that data can be provided to other sources within the organization.
Correct.
Yeah. Brilliant. So you're solving two problems by just simply implementing a DataHub and putting it in a DMZ environment. Right. So let's talk about a case study. Xavier pulled this one up, and this is from wood processing. So can you elaborate on this, Xavier?
Sure. So this was a wood processing facility in the United States. They are using Galaxy servers. One of the things that they do use internally is MQTT. They needed to get that data to an IoT platform and Azure for their data lake. And so their challenge was, how do we do this reliably? So from level 2, they're actually publishing data via MQTT. They have actually 2 Galaxy servers, so they're actually publishing 2 source level datas. The DataHub is actually doing redundancy on the MQTT connections, collecting data from the MES, publishing data to the MES, recording data to the plant historian, as well as now they're pushing the data, or mirroring the data to their admin network that has internet access. So the copies of the data are completely mirrored between the intermediate computer and the network computer, or the admin network. And then from there, they're publishing to their IoT platform, and they're publishing to Azure. So they've actually segmented their networks. There's no inbound firewall ports. There's no VPNs. Everything's completely secured. There's redundancy between the MQTT clients, and it really was a cost-effective and rapid deployment. So they were able to get it up and running in a day. They tested it for 2 weeks, confirmed everything was working great, did some final adjustments, and then bought the licenses.
Perfect. Great. Just to go about the DataHub, and all this latest and the greatest is available by DataHub version 10. And it doesn't only do MQTT or SparkPlug-B or OPC UA, it does a variety of other roles. And what I want to say is the DataHub has been a product in the industry for a very long period of time, working in the critical infrastructure market. So we have got instances of data which is handling more than 2 million tags per instance, right? So it is a very robust, reliable piece of software. Now, this is all from my side and Xavier. We're open for questions, so please feel free to ask us any questions. Our aim was to actually impart some knowledge on the IoT protocols that are being used in the industry to connect plant source data to the cloud. And I hope we've kind of addressed that today. So our goal was to educate you on these protocols, and I hope you're much more wiser about MQTT, SparkPlug-B, and OPC UA, and how they should be implemented and used in the industrial environment. So, unless you've got any questions, Xavier, that you would like to add, anything you'd like to add?
No, I'm good. I'd like to just thank you for your time, and feel free to reach out to Abdul or send us an email. We're happy to assist in any way we can. Perfect.
Right. Thank you, everybody, for your time. And if you've got any more questions, and if you would like to discuss your applications in more detail, then my contact details are here. And the PowerPoint will be shared with yourself, and the recording of this webinar will also be shared. So thank you again, and have a good day. Bye for now.
Bye-bye.